Morning, everyone. Hopefully, everyone's week continues on a good trajectory. Um, just a few notes. The latest worksheet's been posted. It's already on the website and is available. I see some of you have started to do it and have done really well. So just remember, we're back into the groove of having those. And hope I didn't cause too much trouble by giving everyone a break after the exam. Seem to get a lot of emails with that. As a logistical thing, on Friday there'll be a lecture like normal, but it'll actually be posted and recorded by me later today and posted online. I have to travel for a family matter back to Pennsylvania, so I will post it, and you can watch it on Friday during class time or anytime you wish. But I'll almost always try to do synchronous lectures in case anyone has any questions. But for this particular week, I'm going to have to miss Friday, the in-person part of Friday. I will be available for via email for office hours on Friday if anyone has any questions. In the last lecture, we talked about volcanoes, particularly volcanic hazards. Really, where we left off was talking about a particular class of hazards tied to volcanoes from lava flows. We talked about the Aa and the Pahoehoe lava flows. The Aa again being blocky, pretty viscous and slow moving, so really pretty minimal amount of risk of getting sort of run over by that type of flowing lava, but of course it can do great damage to property. And the second example we talked about, or type of lava we talked about, is Pahoehoe, which is the low viscosity, usually tied to a lower silica content and higher eruptive temperature. And those can have really fast flow rates from a few meters per hour all the way up to a few kilometers per, up to 60 kilometers per hour. An example I gave you from the Mount Nyiragongo in the Democratic Republic of Congo during the last class. So without any further discussion of the lava flow hazards, the next thing we're going to talk about is the hazards tied to pyroclastic activity. So pyroclastic activity basically means sort of explosive dust, if you will. This can still be hot and can cause a lot of damage from burns, stuff like that, and often that is the damage people observe. But typically, the major concern with pyroclastic activity is explosive events. So the rock is shattered, ejected at very high velocities, at high temperatures, and that can basically be blasted into the stratosphere of the Earth's atmosphere, which we'll talk about the impacts of that as we go on the lecture today or Friday. And it also can be blasted sort of outward and laterally, like upward and outward laterally, which can have a pretty devastating effect in terms of knocking down trees, destroying homes, property, infrastructure, and things like that. So this picture on the left here is actually from the May 18th, 1980, I believe, Mount St. Helens. This should give you an idea of a lateral blast. And you can see that this is a scenario where the blast is kind of kicking out the side, blowing down slope of the volcano, and also show some photos in a moment here. This did a pretty immense amount of damage for quite a number of kilometers around that area. The other sort of scenario here is, and I should say, and this is basically reminiscent of a situation where the actual volcanic edifice sort of blows up and half the volcanic edifice is lost from this, and often that volcano will collapse upon itself to follow. The alternative is a vertical blast, and that's usually more reminiscent of when the volcano actually stays intact. Maybe there's a silica-rich rock plug that builds up on top of the volcano. The magma chamber comes up and basically has enough pressure to cause the top to sort of blast out and blow its cork. This one can do a lot more human damage in the direct hit. It can, of course, affect the ecosystem in the area, and often can put a lot of ash into the troposphere, which can be carried like by the jet stream and wind patterns, and can deliver ash over great distances. To give you a perspective on this, in 1980 with Mount St. Helens blast, in Ohio and Pennsylvania, you could actually see dust fall, that covered the entire land surface. When that eruption occurred, even that far away from the state of Washington. So maybe it wasn't quite, I'm talking about a sliver of a centimeter, but nonetheless not a there was actually dust covering it this far east. As we'll talk about more as we go along, the vertical blasts tend to be less catastrophic in terms of immediate damage. There still can be dust carried to a lot of different areas, and that dust can cause changes in vegetation, changes in the ecosystem. It can damage soil or plants. It also has a whole, in either case, has a whole suite of human health implications. One is the fact that the ash material is very easily respired, so it can be inhaled and cause a lot of lung damage for individuals that are exposed to it. Often these volcanic rocks and dust dust is what we're specifically focusing on here, is often very metal rich and can cause contamination that can lead to poor water quality, can lead to poor air quality, and can also cause sort of acute metal poisoning. Another factor is that these rocks tend to be rich in uranium, thorium, and potassium, relatively speaking, and as a result, they actually have relatively high levels of what's called naturally occurring radioactive material. So if they're inhaled, they get into the lungs, the dust that gets trapped in the lungs, it's not sort of problem over. That can over time slow decay and cause some health issues, particularly pulmonary issues from this type of material. One of the other aspects of the volcanic hazards, although it ties into the chemical hazard we'll talk about later, is that often this pyroclastic ash will have really high fluoride and sulfate concentrations or minerals in there. And as a result, often when you see rain events that bring the dust back down to surface, people report having skin lesions and burns from the fact that there's hydrofluoric, hydrochloric, nitric, and sulfuric acid that sort of gets mobilized once these pyroclastic debris gets to opportunity to interact with water. The suite of hazards, though, tied to vertical blasts, as we'll talk about as we go on, are more tied to where that dust goes. So vertical blasts tend to go upwards and not directly hit adjacent populations, but it can put a lot of material, particularly fine material, which we can into the stratosphere, which when it gets into the stratosphere can do something called cloud condensation nucleation. You don't even remember that word. What that means is that material actually get into the stratosphere and can help clouds form around it, and those clouds have major climate forcing effects that we'll talk about as we go on today that can cause dramatic global cooling events as a result of these eruptions. And we'll document as we go along the major implications of those hazards. So the key thing here, pyroclastic activity describes an explosive volcanism. The material is both smashed or exploded to extremely small, fine-grained debris, and it is also blown, great distances from a volcanic event into the atmosphere, with the occurrence of direct human implications and dust showing up in local areas and weather being great for lateral blasts, less so for vertical blasts, but vertical blasts can have other implications from dust making its way into the stratosphere. Give you a sense of a pyroclastic activity. If you go to Yellowstone National Park, you can see hundreds of meters thick of pyroclastic debris that sort of was deposited after more recent eruptions. And if you track that out, you can still find multiple meters. That's six or more, 8 feet thick pyroclastic ash deposits from Yellowstone eruptions. As recently as I think 200,000 years ago in places like Kansas and Nebraska. So this has the potential to mobilize an awful lot of material that shows up in, at great distances from the volcanic event. So of this sort of explosive material, you're talking about, little pieces of ash, really just micro-sized rocks. Some of the rocks can be pretty big. There are a whole suite of names around these things I don't expect you to know for this class, but bombs are basically, you can think of it as something that's like a softball to a bowling ball size, so they can get much bigger than that. And that's usually where you see a molten piece of material fly out. Pumice is another example, as well as obsidian or volcanic glass that can be blasted out and shot in a lot of directions. Again, key thing I want you to remember here is they blow into the air, either laterally or vertically. And if you see this material here that's sort of rolling down the side of the volcano, they actually, in addition to being a lateral blast, can also be a pyroclastic flow. And often that will have implications of high temperatures as well. In many cases, volcanoes that have this pyroclastic activity, particularly with a lateral blast and collapse, sometimes the most lasting evidence of their occurrence is actually pyroclastic flows that get welded in place. They're actually so hot they've sort of mineralized and can cover really expansive areas. So if any of you have ever been out to the Valles Caldera area northwest of Albuquerque, it's a really impressive, beautiful area. but the volcano itself is gone from there. But the pyroclastic flows, stretch for dozens of miles and are quite scenic to see. So um, the flow can be a sort of a different kind of component to this. The next component of volcanic hazards, and really these are this is sort of similar in some many ways. The pyroclastic hazards are just ashfall, and the key thing here is that volcano eruptions can cover hundreds or even thousands of square kilometers with a carpet of ash. This is actually the hazard that we observed in Ohio or Pennsylvania, although not nearly as extensive as the ones observed by folks near Mount St. Helens. But this carpet of ash in a relatively small minor volcanic eruption such as Mount St. Helens actually created hazards of dust all over the region. To give you perspective, if you were going to have a sort of a Richter scale equivalent on ash falls, Mount St. Helens would probably be about a 2, right? So there are incredibly larger volcanoes that have actually erupted. Several examples I'll show you today, such as Tambora, that cover the entire world with the ash fallout from their eruptions. So obviously the extent and the potential damage caused by these events are greater the closer you are to the volcano. Once you're getting a little bit of distance from the volcano, not surprisingly, wind directions and the directions of lateral blasts can play a role into where the ashfall will occur. But the obvious things here are immediate destruction of vegetation, destruction of crops, and also destruction of trees. So these can have major implications in the short term for the prospects of having healthy vegetation and your food crops and whatnot. I will say in all these cases, I should have mentioned this with pyroclastic hazards, is that in this case, in pyroclastic or ashfall cases, the long-term implications to vegetation can actually be kind of positive, in the sense that they often deliver key nutrients or critically limited nutrients such as iron and essential metals. But short term they can cause pretty impressive devastation. A big issue is often that reservoirs, lakes, and things that are used for water can often be pretty badly contaminated by ash. This material is really fine grained. It can be difficult to filter out, and often you have to have a pretty long-term, or midterm, weeks to months problem with the surface water contamination. So rivers in general do better within a few weeks, but reservoirs in particular can have a lot of issues with contamination because of the fact this material can, again, includes heavy metals, toxic minerals, as well as naturally occurring radioactive materials. So it takes a while for that material to sort of get deposited out of the water column into the sediments and for the water system to recover. The other factors, particularly within a closer proximity to the volcanoes, is that you can actually see building collapses from the amount of ash that will deposit on the roof. We've had this little calculation here for you. So 1 kilometer of ash accumulation on an average home's roof accounts for about 2.5 tons of extra weight, right? So it's not, it's a lot denser than snow. And as a result, you can think about it as being analogous to the amount of snow, that would come from about 8 inches of snowfall, right? That's a pretty big difference in terms of the weight on your roof. And in areas closer to the volcanoes, that can be pretty profound amount of damage that can result from that. And then the next one with the ash falls, and this is particularly true for eyes, respiratory system, and I should have said skin here as well. Irritation can be a really big issue. Obviously it's pretty clear to see how the dust getting in your eyes or being respired into your lungs would cause irritation, cause tearing of the eyes, or actually can cause lacerations of the cornea. In the lungs, the issue is that it can cause material to build up on the lungs. It can cause what we call reactive airway disease, where the lungs, the cilia start to get sort of damaged and don't function very well, or it can actually just simply overwhelm and cause a respiratory failure. Another additional component beyond the direct interactions with ashfall is that this really fine-grained dust can actually affect airlines. So there's a few examples of this where the volcanic ash is so fine-grained it gets sort of sucked into the grill of the, if you will, of the jet engines, can actually cause the jet engine to stop, and it can shut down. One of the most famous examples here was actually caused by the Redu volcano in Alaska in 1989. There's a commercial airliner flying over that, and basically all four of the engines just completely stopped because there was no air transport coming in to keep the engines cool. The plane, because of that, actually fell about 10,000 feet before the pilots were able to actually get the engines restarted. And as a result, as you can imagine, that's not the only time there's been an issue with this, but it's the most one of the most prolific or most publicized, at least, issues. But if you remember this from back years ago, this is why when there's volcanic eruptions in places like Iceland, it can actually shut down transcontinental flights between North America and Europe, just because there's great fear that this could be repeated, and really there's not much we can do about it. So this is perspective here. Talking about that specifically, some of you may remember this. Probably many of you were still not interested in volcanic hazards at the time. But as recently as April 2010, a large portion of the European airspace is shut down by a 6-mile high ash cloud coming from one of the volcanoes in Iceland, and this caused the closure of American flights for I think almost a few months actually. Again, this was not an exceptionally large ash fall or exceptionally large volcanic eruption by any means, but for perspective, flights were delayed, interrupted, and altered for a few months, but within a 1-week period during the peak of the eruption, over 95,000 flights between North America and Europe and within Europe were canceled, and this led to about $1 billion in costs to the airline industry. So a pretty amazing amount of influence by one relatively small volcano sort of having a hiccup, not even a full-blown eruption. The next component of volcanic hazards is tied to poisonous gases. So this can actually be steam when the water is heated up in volcanic settings or in geothermal vents. The steam can actually can cause acute burns and damage. But mostly when we're thinking about the poisonous gases, unless you're right near a volcanic vent or a geothermal vent, which we call fumarole, F-U-M-A-R-O-L-E, most of the volcanic gases are actually related to these follow-on components that can have different forms of toxicity. So the first two I'll introduce to you are carbon dioxide and carbon monoxide. So carbon dioxide, CO2, carbon monoxide. I think most of us know that carbon monoxide is highly toxic. It binds with the I think it binds with the oxygen carriers, hemoglobin in the body. I'm not totally sure the toxic mechanism, but it causes acute respiratory distress and asphyxiation. And CO2 can have much the same outcome. CO2 basically suppresses oxygen levels below levels where the human body can function and causes asphyxiation as well. So most of these have been very well, most of the volcanic hazards tied to CO2 and carbon monoxide have been very well documented and identified in areas of the East African Rift or in West Africa, in this example. So one of the most famous places where this occurred was in an area called Lake Nyos in the Cameroon. And Cameroon, Lake Nyos in the Cameroon pictured here. What happens is there's an actual lake on top of a volcanic edifice. The volcanic edifice is continuously degassing CO2 from its magma chamber and other gases as well. And what happens is when that gas builds up, it actually dissolves, a fixed amount of that gas can dissolve into the lake's water, and it builds up gas pressure more and more and more. So you can think of it almost like a Coke bottle with a lid on top, but the bottom is chopped off and CO2 is just slowly, bubbling in. There's a point where that pressure builds up and up and up. And, more commonly what happens at CO2 and carbon monoxide, particularly CO2 though, is the fact that something disturbs the water column. That can be a volcanic eruption, it can be an earthquake, it can be a landslide, it can be human activity. But you can think of that lake building the pressure up to the point where it simply, acts like a Coke bottle, and when it's agitated, the CO2 can be displaced from the water, or released from the water in the lake. The important thing here with CO2 is that the density of carbon dioxide is actually, it's mass 44. It's greater than the mass of the ambient air, which is about, a 3-to-1 mixture of nitrogen and oxygen, and it's has a mass of about 29. Key thing here is that 44 is greater than 29. It's more dense, and as a result, the CO2 actually flow right above the land surface and sort of flow out until it mixes with the air and is diluted by the ambient air. And if you're in that plume where the CO2 comes out, gets disturbed out of the Coke bottle, but then hovers along the ground and flows near the base of the volcano, you're in those areas, basically, you have literally no chance to survive. So this is an example. There were dozens of people killed, but also cattle, goats, and everything that were near the area of Lake Nyos when the CO2 overflowed were completely killed. I think the main Lake Nyos CO2 flow over was caused by a minor earthquake from a relatively minor earthquake from a small sort of dike injection or a small subsurface volcanic eruption that caused the area to shake. One of the other concerns is, of course, beyond a physical geological event like a volcanic eruption, a earthquake, or a landslide, is that just simply the amount of CO2 that's bubbling into the lake can eventually exceed the saturation conditions of those gases in water, or the carrying capacity of that water. And that scenario is less about someone taking the lid off the top of the Coke bottle, as it is the fact that once the Coke bottle is totally filled up, more CO2 will cause everything to bubble out. So what you see here on the right is actually a program in a location I'll talk about more in a moment, but on Lake Kivu in the border of Rwanda and Democratic Republic of Congo. So this is the area I worked in previously and mentioned to you in terms of volcanic hazards. But they have a program there where they literally stick a pipe down into the lake. They hook a pump to it, and their whole goal is to basically flow the water up. So when the water comes up, it degasses, and as a result, they can release small amounts of this gas continuously, rather than having a scenario of a catastrophic overturn. So this is actually a picture of Lake Kivu. This is for the record, just south of that volcano, Mount Nyiragongo, and actually Mount Nyiragongo is the bad actor in this situation as well. What happens is in that area there's a continental rift, so the plates are divergent. You have along those rifts lakes that form, where those areas get a lot of, get filled up with water. But that rift from Nyiragongo and the other small volcanoes around there is an actively diverging plate boundary where there's volcanism continuously being emplaced beneath the subsurface in dikes and sills and occasionally eruptions, like you see at Mount Nyiragongo. And as a result, this entire stretch, you can think of this being a long rift that connects all the way from Ethiopia down to Malawi. But in this area, in particular, in the Great Lakes region of Africa, or the Rift Lakes is what people more commonly call them, the CO2 builds up in a lot of places. The area around Mount Nyiragongo and Lake Kivu, as shown here, is relatively narrow and deep, and as a result, it doesn't see as much wind influence in wave action, and it allows a large body of water that is sort of beneath the wind and wave surface of the lake to accumulate volcanic gases. So if you go to that lake, if you were to put a pipe down into the lake a few hundred feet, and that actually goes down to almost 500 meters, about 450, 475 meters in its deepest location, you can actually just have gas blow up, not blow up physically, but blow out of the pipe just because the pressure is so high at depth. So in this scenario, the reason we got involved in working on it was the fact that biologists had recognized there was sort of a 5,000, 6,000, 8,000, depending on the proxy and the author, but some repeated cycle along that time frame of mass extinctions in this valley, where everything seemed to just kind of have a mass death and then things would kind of be rejuvenated. So what folks thought might be going on is that this lake was sort of overturning. The deep gas-rich water was coming up. That CO2 was being released and causing mass extinctions, localized mass extinctions in this area. Not totally clear if that's actually happened or of importance, but the key thing what I'll tell you here is that there is about the equivalent of one year of Africa's energy production in methane that's formed by CO2 being converted by microbes to methane, that CO2 that comes from the volcano, from the rift, being converted to methane, and about 4 times that amount of carbon dioxide that's sort of built up in the lake. So we continuously still monitor this as a potential hazard that can be related to this activity. So every time Nyiragongo, which I showed you last class, actually starts getting more active, more CO2 gets in place along the rift, and there often are these little fish kills, little micro turnovers where the CO2 can kind of come out of there, and that's a common phenomenon for the CO2 turnovers all around Africa. This is in Ethiopia, Djibouti, and Rwanda and Congo. The key thing I failed to mention earlier on is that the addition of this gas below the sort of area affected by wave and wind dissolves a lot of CO2 in it, as I mentioned, but that actually increases the mass of the water in those areas. So it becomes what's called chemostratified, where there's a boundary of denser water below there that accumulates, more gas than it should expected to do so otherwise. And the top area sort of gets recycled by wind and wave action. And as a result, that's one of the things that contributes to allowing so much gas to build up in those areas. For perspective, if this were to overturn catastrophically by an eruption or volcanic hazard, an eruption or volcanic eruption, I mean, this eruption or a seismic activity is what I meant to say, excuse me, and this were to overturn catastrophically, the forecasts are that, this could wipe out everybody in the region. From my perspective, I think that the likelihood of it completely turning over would take a major earthquake or volcanic eruption, and I think more likely scenario is that the scenario of a lot of small hazards are much more likely. Before I go off of this idea of CO2 and carbon monoxide, I'll make the case here is last time Nyiragongo got really active, about 2010, which again, this is north of the lake. Let me just go back here briefly. Go at the map. This is Mount Nyiragongo to the north. This is Lake Kivu here. The whole area is, has the same CO2 and carbon monoxide hazards. And this is actually a volcano that's like Mount Nyiragongo. It's been a little bit, has been inactive for the last few dozen thousand years. One of the things we worked on is that over by the small lobe, there were actually repeated incidences of times where the smaller lakes would turn over, the smaller portion of the lake would turn over, and our sub-basin of the lake would turn over. And for perspective, there was a missionary from Wisconsin who built a school over in this area, had brought kids in from all over this region, which is, we'll talk about this later in the semester, but this region is an area with pretty extreme environmental risks, a lot of migrant and child labor around mining for coltan, which is basically 2 key elements that are needed for most electronics, cell phones, things like that. And as a result, there's an awful lot of artisanal mining, which has a whole suite of environmental problems we'll talk about later in the semester, but is relevant there. And there's a refugee camp that's sort of tied to children that are, saved from that. I went to school, and what we were working on there is that actually there was a scenario where the school kids are playing at the school, everyone's playing soccer after lunch, and within an instant the wind changed direction, and the CO2 actually flowed out of one of these little low-lying areas and caused the shorter children, literally, who were below the CO2 air boundary, to be asphyxiated, and many of them passed away. So the local word for these CO2 winds in that area in Swahili is called the Mazukus, and that means evil winds that people are quite concerned about. Unfortunately, livestock, particularly goats, small ground-running animals, pretty commonly die in this area, die by this method or by this hazard in these types of areas. When we were sampling this, you're often walking up to an area where there's a spring. We have sensors that can allow us to detect this, but you'll often see just a litter of little not squirrels, but little rodents and things like that that'll sort of meet their demise by the CO2. So obviously I worked on that, so I get a little bit excited about it. I apologize if everyone's getting bored of that. But the other volcanic hazard related to gases is in sulfur gas. So SO2 is, if you've ever smelled it, it's really what is stinky. It's the rotten egg smell that can be released when volcanic rock or volcanic magmas start interacting with sulfur-rich rocks on the subsurface, particularly shales, for example. They can release a lot of SO2. And SO2 is not good for you. It's mildly toxic. It's actually fairly toxic. But the thing with SO2 is that you can smell it at a great distance. Okay. In fact, modern gas chromatography and mass spectrometers we use to measure these things can also smell it at measure it at very trace concentrations, but actually don't do much better than the human nose. So the real issue here is that SO2 can cause a series of problems. It's caustic. When that interacts with rainwater or surface water, it can cause so it can become sulfuric acid, can cause burns. It can cause people to go blind. It can denude or remove the vegetation, just like acid mine drainage, and it has a series of problems. But mostly, you don't see this acute asphyxiation when it's an issue of SO2 because people can smell it at a good distance. The opposite is really true for H2S. For those of you who don't know about H2S, or dihydrogen sulfide, it's a reduced form of sulfur, and basically it's relatively rapidly oxidized SO2 in the Earth's atmosphere. But the key thing here is you really can't smell H2S until it's oxidized SO2, and as a result, relatively, chronic exposure has a lot of health problems, but also so does acute exposure to high concentrations. Part of the issue is you just can't smell it, so you're in it in low oxygen air. The other aspect is that it has a whole string of toxic mechanisms that can cause health issues. So there are examples, near volcanoes and also in other aspects of geology. Often, for oil and gas well drillers, it's one of the biggest concerns. We're unwittingly walking into a plume of H2S that's being released into the atmosphere can cause, acute and chronic toxic issues. So, moving away from that, we're going to go on to the next form of volcanic hazards, and that is going to be related to debris and mud flows. So these are particularly common in the Pacific Northwest. It's actually not a direct result of an eruption. What it actually typically involves is loose volcanic ash or other materials such as volcanic bombs or pyroclastic flows. It's accumulated near the edifices of volcanoes. They become saturated with water. They often become saturated with snow melt or actually meltwaters from increased temperatures related to volcanic activity. And what this does is it causes the ash or the pyroclastic material to become saturated, and just like other landslides, start to flow down slope. Here's an example from Mount Rainier in the Pacific Northwest. And you can see here that this is up to about 14,000 feet here. Seattle's off up here. And this actually caused pretty substantial debris flows that flowed, I think something like the order of 60 miles in length, where they flowed down the rivers and the river channels and ended up flowing out into the lowlands of the Puget Sound lowlands and covered a lot of material. Obviously, if you're in the area where this happens, it can be, you can completely remove homes, buildings, bridges, whatnot, and completely denudes or removes all the vegetation, often leaving you with areas that take quite a long time to actually come back to having vegetation, just because the soil profile is completely lost. So one of the key aspects here is that a lot of the particles in this situation are relatively coarse. These typically happen with a material that didn't get ejected and go far away. So often it's material that's hanging around the volcano itself. Those coarse grains, of course, once they get moving, they have a lot of momentum, and you can see that this is an area where it can travel pretty long. The other thing I'll show you here is there's also some other ancient flows. This is not a one-time event in Mount Rainier. This happens every few hundred to few thousand years, and is noted as a hazard now. This is commonly thought of as in terms of rejecting the hazards, is to think about building in areas that are not prone to flooding. So at least that most cases the mud flows do follow the pathways of water, and at least there can be an attempt to avoid the hazard in many locations. So this is what we're going to do now, is just kind of go through a case study of Mount St. Helens and talk about this compendium of volcanic hazards, how one event can actually have a lot of these different types of volcanic activity tied to it. So Mount St. Helens, as you see here, is located, probably you've all heard of this, it's in in sort of southwestern Washington, not very far from the Washington-Oregon border. And this is a picture taken in 1978. You'll notice this looks like pretty much what you think about as a volcano, right? It's actually a composite volcano. And to give you the timeline of how Mount St. Helens got active and led to what we know of the eruption, this is inactive for quite a long period of time. It was recently as March 1980 that it first started to experience seismic activity. I hadn't had any seismic activity or volcanic activity for about 120 years. And then within 2 months, by May 1st, a prominent bulge could be seen forming on the northern flank, which is just up here of the volcano. This bulge actually expanded on average by about 1.5 meters per day, kind of growing. And these things tend to have like a sort of a odd shapes. You can tell pressure is building in those areas. So, for perspective, by May 1, we now recognize with seismic activity, seismic imaging of the earthquakes, that there was a magma body ascending into the base of Mount St. Helens, and this bulge in the northern flank would sort of continuously build up. By May 17th, the day before the eruption really got kicking, there were a series of smaller earthquakes and subsidences where the bulge kept getting bigger and it would slide down the hill a little bit. There's some caldera collapse. So the caldera is the top part where the smoke normally comes out, or lava we tend to think about coming out. And this caldera started to collapse before this. Now, by this point in time, the USGS and the federal government, the state governments had advised everybody in the area to basically get out. Obviously, as you probably have heard, not everybody listened, but within 2 months we went from basically 9 weeks, we went from no activity to this slow creeping, this bulge and slow creeping slide of the collapse of the caldera. And then on May 18th, 1980, preceded immediately by about a 5.1 earthquake at 8:30 in the morning. The eruption started, and there was both all aspects of what we talked about earlier: magma coming out, leading to lava flows, massive pyroclastic eruptions, both vertically and laterally, and the main thing we tend to think about is this sort of lateral blast of pyroclastic material that came out of the side of Mount St. Helens. So within a few seconds later, quite literally, you see this the lateral portion of the volcano blow out. The ash is now cast into the environment at pretty high rates of speed. Lava's flowing behind, lava flows are trailing this ash material, and there's sort of both a lateral and vertical blast that removed about, I think, 20% of the mass of the volcano, during this eruption. So really, really rapid time frame. The amount of material that could be lost. Think about it, just going from this to this, in a matter of weeks. But basically from slow creep and bulge to catastrophic explosion in a matter of seconds, really. So I'll play a video here. Hopefully this will play well and easy to hear of the actual eruption. So this again was taken by the USGS was out of the area, but they had cameras placed in there that they could sort of recover later to see what had happened. Note before we get started, there's already continuous smoke at the top. This area is actually this area here is where most of the bulging had occurred, but this entire area here and out of the screen to the back, out of the image to the back, had actually started slowly collapsing by this point within about a day before this eruption. So notice how quickly this is moving. This is all still failure of the slope, and here's the first eruption. So notice the vertical blast is starting, lateral blast is starting. And at this point, even at the end of this here, we still are not observing any lava flows. In fact, there's no imagery of actual lava flows, but later people observed, when things calmed down, people went in there and observed the lava flows to actually determine that they were part of the equation as well. So clearly this is a really rapid, fairly catastrophic situation. to go through the timeline of what happened, you had a 5.1 earthquake that kind of preceded everything. Mount St. Helens started to experience slope failure, beginning of a lateral blast from the bulging area or adjacent to the bulging area, and that was sort of immediately or sort of synchronously attached to a vertical blast. For the perspective, the blast moves at about 1,000 kilometers per hour, which is 600 kilometers per hour is I think about the speed of sound. I'm not sure I'm right about that, but that's pretty close to right, I think. So you see the speed of the material going about 1,000 kilometers per hour, and the main force of that debris was observed for over at least 30 kilometers from the volcanic edifice itself, where this material just immediately shot out at about 1,000 kilometers an hour. Key thing here is that really beyond that zone, that's where all those sort of ashfall and other hazards become relevant. But within that zone, you're talking about direct lava flows, certainly pyroclastic blasts, pyroclastic flows that sort of immediately wipe out everything within that path for about 30 kilometers. After the lateral blast, this is when the large vertical cloud started to be observed. Basically, for about within the first hour, the vertical ash blast had reached an altitude of about 19 kilometers above the volcano, and that level of eruption and pyroclastic ash vertical blasting to those elevations lasted till for about 9 hours after that. So, into the afternoon. And in the end, the ejected material from ash flows and ash clouds totaled about 1 cubic kilometer of rock released during this event. For perspective, that's actually a relatively small, again, volcano, not really something that would be, if it wasn't the United States and heavily covered by the media with cameras right there, it probably wouldn't have been something we saw reported on the news in most of the places in the world. And then after that ash and even a bit of lava flow, the volcano is about 450 meters shorter, about a half kilometer shorter. And then about 400 square kilometers were completely devastated by debris, the lateral blast and mud flows. I don't know if any of you have been there or if any of your families have visited this on family vacation or whatnot. If you go there today, is still a very obvious difference in the area where it experienced this debris flows and where the trees have been totally wiped out. So there were 54 people directly killed. The numbers of deaths attributed to this are above 100 from people who experienced pulmonary distress and other factors related to this. Amazingly, largely because it was in a fairly rural area, only 100 homes were destroyed. But even in 1980 dollars, damage was estimated at about $1 billion from this volcanic eruption in an extremely a low population density area. So imagine if this happened in an area closer to Seattle where the lateral blast went in that direction. Obviously that would be fairly unlikely based on what the volcanic activity in those areas. But most importantly, it would be could be incredibly devastating. $1 billion of damage in one of the more rural locations this could have happened. So again, for perspective, an hour later, the full vertical eruption got going. That's where it reached the 19 kilometers. The pyroclastic flow had already sort of started to mineralize and sort of become solid in those areas. Ash flows continued on top of it and accumulated material for quite some time. Here's some helicopter imagery of the vertical eruption. This is taken from a good distance away. I don't know exactly what it is, to be honest, but here's your perspective, just how expansive this was. Putting it all in perspective, the main edifice of the volcano is here. This is the area covered by the sort of welded pyroclastic flow. There's a sort of bunch of debris avalanches. This orange is the area that was down to timber just by the debris flows and also the sort of shock waves and whatnot around it. And of course, one of the biggest hazards, I don't have a video of it for today, but you might have seen, is there also were mud flows or mud debris flows that went down most of the rivers and actually wiped out bridges dozens of kilometers away from the actual volcanic edifice. So I mentioned the ash flow. from this volcano, reaching all the way to the northeast. You can see the sort of falls, same patterns of the jet stream, but basically this area gives you a sense of the actual like high degree of pyroclastic material and flow. And this is the path of the ash cloud, which made its way across the United States and actually, again, was observed in Ohio, Pennsylvania as dust on the ground from this eruption. People could go out to their, had to go out and clean their windshields off of this debris after, after it made its way through. So, this is an example. This is an airport hangar, small airport hangar. I think I remember this being told this is about something like 100 kilometers, 90 kilometers away from the eruption. You can see that the horrifyingly scary ash cloud that's blowing over the top of the area. This is eastern Washington, where people had to get out and get shovels to sort of clean their walkways off, almost like it was snow of ash debris. And you can see this is just the roads where people are, hate to be this guy over here, getting that dust blown in his face. And this gentleman obviously seems to have some cognizance of the fact that there's some major health implications to breathing this in, and seems to be largely avoiding this by wearing the mask, which we're all too familiar with these days. So from a perspective of showing what the volcano looked like before, this is pretty immediately after. I think this is later this summer in that year. You can see this is basically completely denuded, no vegetation, covered by recent vegetation that's been covered by recent debris that's covered the vegetation and hasn't really been planted or habitated later. And you can see this is the area where we lost about 450 meters of rock and debris flew out the side. So this is sort of immediately after the eruption. But notice this is 10 years later. We still don't see the trees coming back. They're not exactly up by the volcano there, but they were off in this area. You can still go there into the parks and see major trees have been blown down. You do see vegetation, flowers, and sort of low ground vegetation coming back in those areas. Now I was there in 2018, and there is more vegetation than this for sure now, but it's not exactly anything like the amount of trees we saw in the area before the eruption occurred. So I'm gonna end the lecture there for today. It's almost 10 o'clock, and I'm gonna again wrap up the lecture on volcanoes this week on Friday, talking about the role of volcanoes in society. The key things that I mentioned again is that I have to travel on Friday, so the lecture will be posted probably this afternoon, and will be ready for Friday. I encourage you to watch it whenever it's convenient for you, but there will not be a live lecture on Friday. Or synchronous lecture on Friday. There'll just be a lecture that would have occurred on Friday that'll be on Zoom and tape for you to watch. I really apologize about that, but have to travel because of a family matter. I hope if I don't talk to anyone in person, I hope everyone has a good week, and look forward to connecting with you in person on Monday morning. Thank you very much. Have a good weekend.